Welcome to today's class. Today we're going to cover relation between temperature and the resistance. Let's start with the resistance. What is resistance is? Resistance is fundamentally the ability of a material to restrict the passage of electric current. Why? The resistance is changes when in change with temperature. So does the resistance. The TCR, temperature coefficient of resistance, TCR, is very important and fundamental phenomenon for electrical and electronic circuit. When TCR is high, it means that the resistance changes significantly. So if resistance changes significantly, it means the circuit is unstable. But when TCR is low, it means that R is not changes, and this is actually used in precise components such as manganese. Let's write manganese and constantan. These actually are the alloy of electric conductor. We are not discussing about these things. Let's start with the TCR. So what is actually TCR is, and let's describe mathematically. Let's consider at 0 degree Celsius temperature, the reference. Let's consider this is the reference temperature, and in that temperature the resistance is R naught, right? Now temperature increased up to T theta. So at 0 degree Celsius the temperature consider T naught, and temperature increased up to T theta. It could be any value. We are not considering that value. And at T theta temperature, let's consider the resistance increased at R theta. So the empirical equation of TCR will be R theta is equals to R naught 1 plus alpha into the changes of temperature. So temperature changes, the large one is T theta minus T naught. So we could write down R naught 1 plus alpha, and the temperature changes, let's write down T del of T, right? From the equation we could write down the TCR, or temperature coefficient of resistor or resistance, whatever. So alpha is equals to, we could write down change of resistance over the initial resistance and the temperature difference, right? So what is the significance of the parameters of TCR? So R naught is the initial resistance, and R theta is equals to the final temperature, and alpha is equals to the temperature coefficient of the resistance, which actually indicate how much the resistance changes per degree of temperature changes, right? And del T refer the change of temperature. So this will be T theta and this will be T naught. And of course the del of R is also refer the change in resistance. Change in resistance. Let's start with an example. A copper wire has a resistance 20 ohm at 0 degree Celsius. So as we explain the theoretical part, so 0 degree Celsius temperature, the resistance is 20 ohm, and temperature enhanced or increased at 50 degrees Celsius. At that time I mean at 50 degrees Celsius temperature, what will be the resistance that we have to calculate. And for the copper wire, the TCR, the value of temperature coefficient of resistance alpha is equals to 0.004 per degree Celsius. So these are the given data to solve the problem. So what is the equation to solve this problem? R theta is equals to R naught 1 plus alpha into del T. So the temperature initial is 0 degree and the final one is 50. So del theta is nothing but 50 minus 0. So this will be 50. And the value of alpha is nothing but 0.004 plus 1. And the value of initial resistance is 20. So R theta is equals to, so we could compute by using calculator. R theta is equals to 24 ohm. So at 0 degree Celsius, the temperature was 20 ohm. 50 degree Celsius, it means after increasing the 50 degree Celsius, the resistance increased 4 ohm. Hope you understand. Let's start with the another example. Example number 2. The resistance of tungsten filament bulb 27 degrees Celsius, resistance is 100 ohm. It means that when the temperature is 27 degrees Celsius, in that case, the resistance, let's say this is R1, is equals to 100 ohm, right? And the temperature coefficient TCR alpha is equals to 0.0045 per degree Celsius. Calculate the resistance of the filament when temperature goes to 2 to 7 degree Celsius. So the final temperature R theta is R theta is equals to what we have to calculate, and this will be the final temperature. T theta is equals to 2 to 7 degrees Celsius, right? But the equation we have to solve, that is R theta is equals to R naught 1 plus alpha del T, right? So what is exactly R naught is? It means the reference resistance is not given at this question. So R naught means here R naught when it is 0 degrees Celsius. So at 0 degrees Celsius, the reference resistance is R naught. That we have to calculate first. Then we can calculate the final value, which one actually asked in the question, right? So R naught, if we calculate the value of R naught, we have to compare within this value. So if we can write down R1 is equals to, the initial one is R naught 1 plus, of course, the value of alpha TCR dot the temperature difference, this one, right? So we have to calculate the value of R naught to calculate the final result of R theta. So R naught is equals to R1 over 1 plus alpha del T. So let's plug in the value. So what is the value of R1? R1 is equals to 100 ohms, and of course here 1 plus 0.0045, and the temperature difference 27 minus 0, so this will be 27, right? So the result will be 89.1663 ohms, right? Now plug in the value here, 89.166, 1 plus 0.0045, and the temperature difference is what? 227 minus 227 minus 27 degree. No, here will be 0 because we have taken the reference is R0. So here will be 0, right? Not 27. Careful. And here will be the first bracket close. So after calculating this one, we will find the value of R theta is 169 ohms, right? So this is the final answer. So let's recap this one. So the temperature 27 degrees Celsius, 100 ohms, and we have to calculate the temperature 227 degrees Celsius, that will be 169. So at very early stage, the resistance was, let's use the red one. So the resistance was here is 89 ohms, right? So temperature increased up to 27, it becomes 100, and more temperature up to 227, the resistance become now 169 ohms. Hope you understand. If any question, please give a comment on the comment section. Thank you. Let's summarize the topic. So the TCR, temperature coefficient of resistance alpha, is equals to, we could write down, change of resistance over the initial resistance, which is R0 at 0 degrees Celsius, and of course the temperature difference, that is del of theta, right? Now we can use actually this resistance in 3 different type of circuits, such as for metal, for long distance electric power transmission. So for metal alpha always positive, which is very important, that for metal alpha always positive value, right? And resistance is increase with the temperature increase. For semiconductor alpha is negative, and resistance decrease with the temperature decrease. For alloy, so the best example of alloy is manganese and constantan. So for alloy, alpha is very small, alpha is very small, and resistance always constant. It means that at alloy resistance are not changing, so this is constant. And for alloy, as I said, manganese and constantan is literally used for high precision applications such as resistance standard for industrial use and ammeter shunt and thermocouples. Literally we are used this type of fact alloy are using, right? So this is the end of this topic. If any question, please give me a comment, I'll explain more. And of course there are some more details coming in next lectures where we can discuss more about graphs and many more maths, and obviously this depends on your comments. Thank you so much. Have a good day.